What happens when something from the darkest depths of the universe begins to behave in ways that no scientist on Earth expected? Tonight, dear listener, stay until the end, because what is happening in our sky could forever change the way we understand the cosmos and our place within it. Good evening, dear listeners. Felipe Suarez here, accompanying you on this starry night from the booth you know so well. Have you ever thrown a stone into the air and expected it to change course on its own? Because that, in essence, is what we are witnessing with this cosmic visitor called 3I Atlas. I know it sounds impossible. I know it seems like something out of a science fiction movie, but the data is there. The images do not lie. What will happen when this object reaches the vicinity of Jupiter in 3 years? Join me to find out. Just a few weeks ago, in the beating heart of Mexico City, a telescope operated by amateur astronomers with decades of experience captured something extraordinary. It was the night of December 23rd, a date that for many Mexicans means Christmas preparations, family gatherings, and the aroma of punch warming on the stove. But for a small group of dedicated observers, that night meant something completely different. It meant pointing their instruments toward the night sky, toward a specific point where they knew something unusual was occurring. The comet 3I Atlas had reappeared after its passage behind the Sun, and the first images they obtained that night left everyone present in a state of absolute silence. It was not the silence of disappointment nor the silence of boredom. It was the silence of genuine astonishment, that moment when words simply are not enough to describe what the eyes are processing. The images showed structures that should not exist according to conventional cometary models. Tails extending in impossible directions, glows fluctuating without apparent reason, and an anti-tail so defined, so perfectly traced, that it seemed drawn with a ruler and compass across millions of kilometers of empty space. The team worked for hours processing the data, verifying each pixel, making sure there were no errors in the instruments nor artifacts in the photographs. When they finally confirmed that what they were seeing was real, they knew they had something important on their hands. Something that the international scientific community needed to know immediately. But to truly understand the magnitude of this discovery, one must first understand what exactly 3I Atlas is, and where this mysterious visitor that has captured the attention of astronomers around the world comes from. The comet 3I Atlas is not an ordinary visitor. It was not born in our solar system. It did not form in the Oort cloud, that frozen sphere of billions of comets that envelopes our system at distances that surpass anything we can easily imagine. Nor does it come from the Kuiper belt, that ring of frozen objects beyond Neptune's orbit, where Pluto and its smaller siblings orbit in eternal silence. This object traveled distances that the human mind can barely conceive. It crossed the void between the stars for millions, perhaps billions of years, moving through the absolute darkness of interstellar space, where the temperature barely exceeds absolute zero and the light of the stars is so faint that it barely constitutes a whisper in the immensity. And then, finally, after that unimaginable journey, it arrived in our cosmic neighborhood. It crossed the invisible border that separates interstellar space from the Sun's sphere of influence, and began its descent toward the interior of our planetary system. Astronomers detected its presence for the first time several months ago, when it was still at enormous distances from us. The large robotic telescopes that patrol the sky searching for near-Earth objects captured its faint glow, barely a point of light among millions of stars, moving against the stellar background in a way that revealed its foreign nature. The orbit it traced was hyperbolic, not elliptical like that of comets belonging to our system. This meant one clear and unequivocal thing. This object was not gravitationally bound to the Sun. It came from outside, would pass through our neighborhood just once, and then would continue its journey toward the distant stars, never to return. It was only the third confirmed interstellar object in the history of modern astronomy. The first had been the famous Oumuamua, detected in the year 2017, an elongated and strange object that puzzled scientists with its cosmic cigar shape and its inexplicable acceleration. The second had been the comet 2I Borisov, discovered in the year 2019, an object that behaved more conventionally and that reassured those who feared that interstellar visitors were all as enigmatic as Oumuamua. But 3I Atlas turned out to be different from both. From the moment the first orbital data were processed, it began to show behaviors that defied everything we believed we knew about comets and about the laws that govern the movement of celestial bodies in the universe. Do you realize what this means, my friends? We thought a comet was simply a ball of ice drifting, following the laws of gravity like any other object in space. But 3I Atlas is telling us that maybe it is not so simple. What kind of natural force can produce such precise adjustments in a trajectory? There is something we are not seeing, something our instruments cannot detect yet. I promise you that the further we advance in this story, the more fascinating it gets. Are you ready for what is coming? The most recent images captured by the team of astronomers working tirelessly in Mexico City revealed something that left the scientific community in a state close to astonishment, mixed with a deep unease that few dare to admit publicly in conferences or academic publications. The trajectory of this comet, according to the most precise calculations available, experienced an adjustment. Not a chaotic deviation caused by random forces, not a casual push from the solar wind as happens with so many other objects that traverse space. It was a precise change, almost millimetric in astronomical terms, that placed it on a direct encounter route with Jupiter's Hill radius. To understand the magnitude of this finding, one must first understand what exactly the Hill radius is. Imagine an invisible zone around any massive planet, a subtle border where that world's gravity begins to dominate over that of the Sun. It is like its own territory, a gravitational kingdom that separates a planet's influence from the influence of our mother star. Jupiter, being the undisputed giant of our system, possesses an enormous Hill radius that extends for more than 53 million kilometers in all directions. It is a region of space so vast that it could contain Earth hundreds of times without the slightest problem. Within that invisible sphere, Jupiter is the absolute king. Its gravity dominates over any other influence, capable of capturing moons, deflecting asteroids, and forever altering the destiny of any object that ventures too close. And 3I Atlas, after that mysterious adjustment in its trajectory, is heading exactly toward that edge. Not near it, not in its general proximity, but exactly toward it. The precision is of the type that makes astronomers stop what they are doing, review their calculations 2 and 3 times, and then look for errors that simply are not there. It is the type of precision that defies statistical probabilities in a way that is profoundly uncomfortable for those who prefer simple and conventional explanations. When a scientist sees something like this, their first reaction is to assume there is an error somewhere, that the instruments failed, that the processing software has a bug, that someone entered a wrong data point at some step in the analysis chain. But when multiple independent teams, using different telescopes, different methodologies, different data reduction programs, all reach the same conclusion, then one must accept that what is being seen is real. And that is exactly what has happened with 3I Atlas. Observatories in Chile, in Spain, in Hawaii, in Australia, all confirming the same anomalies, all scratching their heads with the same perplexity. But here comes the part that truly keeps those who study these phenomena with dedication and rigor awake at night. That adjustment did not occur when we could observe it. It happened when the comet was behind the Sun, completely invisible from Earth, out of reach of any terrestrial or space telescope we have operational at this moment. It was as if the universe had decided to deliberately hide the exact moment when something extraordinary happened. As if a cosmic curtain had closed just at the precise instant when we needed to be watching. When the object finally reappeared in our field of vision, emerging from the solar glare like a swimmer coming to the surface after holding their breath too long, and scientists updated their orbital models with the new data, they discovered that something, whatever it was, had pushed the comet just enough to radically change its destiny. The odds of this happening by pure chance are astronomically low. We are talking about 1 in a billion, perhaps worse. It is like throwing a dart from 100 meters away blindfolded, in the middle of a windstorm, and still hitting right in the center of the target. That is exactly what this interstellar visitor has just accomplished, and no one can explain how it did it. Had you ever thought that a comet could behave like this, friends? Neither had I confess. And believe me, I have spent many nights behind this microphone telling you about the wonders of the cosmos. But this is different. This has a different flavor, a texture I had not felt before in any space story. Could it be that we are witnessing something that will change astronomy books forever? What do you think can explain this impossible precision? Stay with me. We still have much to discover. When a celestial object changes course unexpectedly, scientists seek explanations within the framework of known physics. It is the natural procedure, the path that science has followed for centuries to understand the mysteries of the universe without resorting to supernatural or fantastical explanations. The first candidate, the most obvious and studied, is outgassing. Comets are composed mainly of ice, dust, and volatile compounds that sublimate when they approach the Sun. When solar heat penetrates the frozen surface of a comet, those ices do not melt as they would on Earth. In the vacuum of space, they pass directly from the solid state to the gaseous state, creating jets of vapor that escape violently outward. Those gas jets act like small rocket engines, pushing the comet in directions that may seem unpredictable, but that follow identifiable patterns when analyzed in sufficient detail. It is a well-documented phenomenon, observed in dozens of comets over decades of meticulous study by dedicated astronomers. Scientists have developed sophisticated mathematical models that can predict with reasonable precision how outgassing will affect the trajectory of a given comet. Knowing the composition of the nucleus, its size, its rotation speed, its distance from the Sun at each moment, they can calculate how much thrust it will receive and in what direction. But here is the fundamental problem with that explanation when we try to apply it to 3I Atlas. Outgassing produces chaotic pushes, not precise adjustments. It is like trying to park a car by blowing on it with an industrial fan. You could move it, no doubt, but you would never place it perfectly in the designated space, aligned to the millimeter with the lines painted on the ground. And yet, that is exactly what appears to have happened with 3I Atlas. The push was of the exact magnitude, at the exact moment, to place it on a trajectory that will culminate in March of the year 2026 with a close encounter at Jupiter's gravitational limit. It is the type of coincidence that makes even the most skeptical scientists begin to scratch their heads with genuine perplexity, searching for alternative explanations that simply do not appear no matter how hard they try. The images captured from Mexico City also reveal another intriguing element, something that adds an additional layer of mystery to this cosmic enigma that grows with each new observation made from any point on the planet. 3I Atlas not only changed its course inexplicably, it is also exhibiting a completely anomalous tail structure that defies the models established during decades of intensive cometary research. Comets, as many know, develop spectacular tails when they approach the Sun's solar radiation and the stellar wind push dust and gas away from the nucleus, creating those luminous trails that have fascinated humanity since time immemorial. Our ancestors saw them as omens, as divine messages written in the night sky, announcing wars, plagues, or the birth of kings. Today we know they are perfectly natural physical phenomena, the result of the interaction between cometary material and the energy of our star. Fine dust is pushed by the pressure of sunlight, forming a curved and diffuse tail that roughly follows the comet's orbit. Ionized gas is accelerated by the solar wind, forming a straight and bluish tail that always points directly away from the Sun, regardless of which direction the comet is moving. But 3I Atlas has something that very few comets show. Something that has puzzled observers since the first weeks of intensive tracking. An anti-tail. A tail that points toward the Sun, not away from it. Wait a moment, friends. Let me make sure you understood what I just said. A tail that points toward the Sun. Do you realize how strange that sounds? It is like telling you that I found a river that flows uphill, or a flame that freezes instead of heating. Comet tails always point away from the sun. That is the basic rule. So what the hell is happening with 3I Atlas? How can it defy something so fundamental? This anti-tail phenomenon, although rare, is not completely unknown in cometary astronomy. It occurs on exceptional occasions when heavy particles remain suspended along the comet's orbit, and from a certain observation angle they appear to form a tail that defies apparent logic. It is a perspective effect, nothing more. Or at least that is what it should be according to all the models we have developed over decades of careful study. But here is what truly has astronomers around the world fascinated. The anti-tail of 3I Atlas is too narrow, too defined, too stable. It looks as if someone had traced a straight line with a laser across millions of kilometers of empty space. And that, according to the physical models we have, simply should not be possible under any known natural circumstances. When a comet releases dust into space, that dust should disperse in a predictable manner. The sun's gravity pulls particles toward the center of the system. The constant pressure of solar radiation pushes them outward. The small gravitational perturbations caused by nearby and distant planets deflect them in random directions. Everything contributes to the particles spreading in a broad and diffuse pattern over time. It is basic physics, celestial mechanics that we have understood and used to predict the behavior of countless objects for more than 3 centuries of rigorous astronomical observation, from the times of Newton and Kepler to our days. But the anti-tail of 3I Atlas does not behave that way. It looks ordered. It looks intentional. It looks as if something were keeping those particles in perfect formation across distances that defy the human imagination. And that raises a profoundly uncomfortable question for the scientific community. A question that many prefer to avoid, but that is inevitable when analyzing the data honestly and without prejudice. What natural force can maintain such a precise structure across such vast scales? Is there some physical mechanism we have not yet discovered? Or are we facing something that transcends conventional explanations? Astronomers have proposed several theories to try to explain this anomaly, working day and night to find answers that satisfy the demands of the scientific method without needing to resort to extraordinary hypotheses. Perhaps the comet's composition is completely unusual, with types of ice that sublimate in ways our models do not yet correctly capture. There are many varieties of ice in the universe, not just the water ice we know on Earth. There is carbon dioxide ice, carbon monoxide ice, methane ice, nitrogen ice, and dozens of other frozen compounds that could behave in surprising ways when heated by solar radiation. Perhaps there are magnetic fields involved, electromagnetic interactions between the cometary dust and the solar wind that our equations still do not describe with sufficient precision. Interplanetary space is full of invisible magnetic fields, lines of force that connect the sun to the edges of the solar system, and that can influence the movement of charged particles in complex and difficult-to-model ways. Perhaps the internal structure of the nucleus is so irregular, so different from any comet we have studied before, that it produces perfectly directed gas jets that create apparently artificial patterns, but that actually obey natural processes we simply do not understand yet. All of those are possible explanations, and scientists are working with every available piece of data, every captured image, every spectroscopic measurement, to determine which of them, if any, can explain what we are observing. But here is the fundamental problem that none of these theories can completely solve. None of those explanations fits perfectly with all the observations. Every time it seems that a theory works to explain one aspect of 3I Atlas's behavior, a new detail appears that does not fit, a piece of the puzzle that simply does not match the rest of the picture. It is as if 3I Atlas were playing with us, friends, revealing clues here and there, but never showing the complete picture. And that is precisely the frustrating, but also fascinating part of all this. Every time we think we are close to a definitive answer, a new piece of data appears that complicates everything. Could this comet be made of materials we have never seen before? Does it come from an environment so different from ours that its physical processes resemble nothing we know? Will we ever come to understand it completely? Observations made in recent weeks have revealed significant changes in the color of the coma surrounding the comet's nucleus. It is a detail that might seem minor at first glance, but that has profound implications for our understanding of the nature of this object. Before perihelion, that point of closest approach to the Sun where the comet receives the greatest amount of heat and radiation, the coma showed a characteristic reddish hue. It was a color that astronomers recognize well, associated with certain types of organic compounds and minerals that preferentially reflect light at the longer wavelengths of the visible spectrum. But approximately 4 weeks after perihelion, when the comet had already begun its journey back toward the outer regions of the solar system, images obtained by a large telescope 8 meters in diameter began to show the halo with a distinctive green coloration. It was a dramatic change, visible even in photographs without the need for special analysis instruments. This color change is not a minor detail nor an unimportant curiosity that can be dismissed as an observation artifact or a processing error. The green tone is a strong indicator of the presence of molecules like diatomic carbon, those pairs of carbon atoms bonded together that emit light in that specific range of the electromagnetic spectrum when excited by solar radiation. In practical terms, this means that the molecular composition of the coma changed after the passage through the intense heat near our mother star. Something happened inside the comet's nucleus, or in the surface layers of material surrounding it, that fundamentally altered the chemistry of the gases it was releasing into space. This type of change implies chemical and dynamic processes occurring at scales that still need to be measured and fully understood. It is not simply that the comet is releasing different types of material as it heats up and cools down. It is something more complex, more dynamic, more difficult to explain with the simplified models we habitually use. It is as if the comet were a living organism, responding to changes in its environment, adapting to variable conditions as it moves through the solar system. Of course, scientists do not literally believe the comet is alive. But the metaphor is useful for capturing the sense of complexity and dynamism that this object is exhibiting. Another relevant point that has captured the attention of the most meticulous researchers is the X-ray emission associated with the interaction with the solar wind. Space instruments sensitive to this wavelength observed brightness coming from the region around 3I Atlas, a signal that reveals energetic processes occurring at scales that surpass anything that normal comets produce. The most plausible mechanism, already studied in other comets, involves the interaction between the solar wind and the gases released by the coma. When solar wind ions, those charged particles that constantly flow from the Sun's corona at speeds of hundreds of kilometers per second, collide with neutral molecules of cometary gas, charge exchanges occur that generate emission in the X-ray range. What stands out here is not simply the existence of X-rays, something that has been observed in other comets before. It is the observed extent of this brightness. According to data published by various research teams, the range and spatial distribution of the X-ray emission are considerably greater than expected for a typical comet with a similar visual appearance. It is as if the object were radiating energy at scales that exceed the predictions of our current models. As if there was something additional happening, some energy source or some amplification mechanism that our equations do not contemplate. Does it not seem strange to you, friends? X-rays are not something we can see with the naked eye, but our space instruments detect them clearly, and the amount that 3I Atlas is producing is greater than it should be. Much greater. What is really happening up there? That is the question that keeps me awake. Because when an object produces more energy than our models predict, there are only two possibilities. Either our models are wrong, or there is something in that object that we are not understanding. Which do you think is the answer? There is also the matter of the visual scale of the observed structures. Recent images cover enormous regions around 3I Atlas, spanning from hundreds of thousands to millions of kilometers. This provides an important physical context that should not be overlooked when trying to understand the nature of this cosmic visitor. The observed structures are not local details nor small irregularities that could be attributed to photographic effects or data processing. They are massive features that occupy volumes comparable to the largest interplanetary systems we know. When we talk about comas and jets extending millions of kilometers into space, we are not dealing with small surface variations. We are facing phenomena that require considerable sources of energy and mass. Sources that our current models have difficulty explaining satisfactorily, without resorting to assumptions we have not been able to verify directly. The distribution of dust around 3I Atlas presents another mystery that has the most experienced specialists in cometary physics perplexed. In a typical comet, we expect to see a clear separation between fine particles and coarse particles, a natural stratification that results from the different forces acting on grains of different sizes. Fine dust, being light, is quickly pushed away from the nucleus by the pressure of solar radiation. Each photon of light that strikes a microscopic particle transfers a small impulse to it, and when billions of photons strike billions of particles every second, the cumulative effect is considerable. The smallest particles are accelerated rapidly, moving away from the comet to form the diffuse and curved dust tail that we observe from Earth. Coarse dust, being heavier, remains closer to the original orbital path. The same amount of photons produces a much smaller push on a large particle, so these tend to lag behind, forming a trail along the comet's orbit that can persist for years or even centuries after the comet has passed. Over time, this separation becomes very evident in observations, allowing astronomers to clearly distinguish between different types of material and deduce information about the composition and structure of the cometary nucleus. But in 3I Atlas, this separation is not as clear as it should be. There are regions where fine dust and coarse dust appear homogeneously mixed, as if they had been released at the same time from the same region of the nucleus, but then behaved in completely different ways than expected. It is a pattern that defies our models of cometary dust emission in fundamental ways, forcing researchers to rethink assumptions they had taken for granted for decades of accumulated work. And when scientists say that something does not fit, they are not talking about small discrepancies that can be adjusted with a bit of advanced mathematics. They are talking about differences that force reconsideration of the most basic assumptions about how these objects work and what physical processes govern their behavior. 3I Atlas is an interstellar object, which means it forms somewhere completely outside our solar system, perhaps around a star very different from the Sun. A cold red dwarf whose light barely warms the planets that orbit it, where temperature conditions are so different that the ices that form have completely different compositions from those we know. Or perhaps a blazing blue giant whose intense radiation creates conditions that do not exist anywhere in our cosmic neighborhood, where the chemistry of planetary formation follows paths we have never directly observed. Perhaps it formed in a region of the galaxy where the conditions of temperature, pressure, and chemical composition were radically different from those that existed in the primordial nebula that gave origin to our own solar system approximately 4,500,000,000 years ago. Think about it for a moment, friends. This object comes from another place, literally from another stellar system, perhaps from another region of our galaxy where the rules are different. Does it not give you chills to think about that? It is like receiving a letter from a country we have never visited, written in a language we can barely decipher. What secrets does 3I Atlas carry with it? What can it teach us about the distant corners of the cosmos that we will never be able to visit personally? These questions keep me awake every night. The public reaction to these discoveries has been immediate and intense, as was to be expected in an era of instant communications and social media that amplify both legitimate information and misinformation. In live broadcasts and on digital platforms, severe criticism has emerged toward the agencies that published the images. Some people even accused the official images of manipulation or charlatanry, suggesting there was something that institutions wanted to hide or distort. There has also been distrust regarding the successive adjustments of orbital parameters published by official organizations. Every time scientists refine their calculations with new data, some interpret it as evidence that they are changing the story to fit some hidden narrative. Among the most repeated points in the public debate, there are issues that deserve serious scientific attention, rather than ideological or conspiratorial polarization. One of them is the difference between raw data and processed images. Adjustments in contrast, filters, and mosaics can alter the perception of color and the extent of observed structures. What appears intense green in a processed image could be faint green in the original data, or vice versa. Without access to raw data, it is difficult for independent observers to verify the claims of the teams publishing results. Another point is the successive corrections of orbital parameters. These corrections are normal in astronomy, since each new observation refines our understanding of an object's trajectory. But they should be accompanied by clear documentation on methods and uncertainties, so that anyone with appropriate technical knowledge can verify the calculations and confirm or question the conclusions. There are also disputes about composition, with observers noting that some reports avoid direct statements about certain elements, limiting themselves to cautious interpretations. This generates distrust when the data is not open and accessible for independent verification. This public criticism serves as a reminder that scientists and observatories need to publish not only the final images, but also the initial data and processing steps. Only then can the debate move from speculation to the realm of empirical verification that characterizes genuine and productive science. When accumulated observations do not fit existing models, there are three possible paths the scientific community can follow. The first is to look for instrumental or processing errors. Perhaps the telescope has a defect. Perhaps the reduction software has a bug. Perhaps someone entered incorrect data at some step in the analysis. It is important to rule out these possibilities before drawing dramatic conclusions. The second path is to adjust physical models with testable hypotheses. Perhaps the cometary physics we know is incomplete. Perhaps there are processes we have not considered. Science advances when data forces us to modify our theories to accommodate new observations. The third is to consider bolder alternatives if the previous hypotheses fail. If after searching for errors and after trying to adjust conventional models the data still does not fit, then one must consider possibilities that may seem speculative or even extravagant. This includes, yes, the possibility of artificial origin. The problem arises when one jumps directly from searching for errors to final declarations without going through the complete testing process. Loeb makes clear that recognizing anomalies is not a scientific weakness, but the starting point for learning. He does not demand definitive conclusions, but rather that the data be analyzed without forcing it to fit a previous narrative. And here we are, my friends, navigating together through unknown waters. Because that is exactly what 3I Atlas represents for us. An unexplored ocean of which we can barely glimpse the surface. But allow me to ask you a question that has been going around my head since I began investigating this case. What would happen if this object is not simply a chunk of ice and rock wandering through the cosmos? What would happen if, against all reasonable expectations, we were witnessing something that transcends our current understanding of what is possible in the universe? I'm not saying it is so, friends. I'm just raising the question that many have on the tip of their tongue but don't dare to pronounce out loud. The international scientific community finds itself at an inflection point regarding 3I Atlas. In renowned universities, in space research laboratories, in observatories situated on the highest peaks of remote mountains, groups of researchers work tirelessly to unravel the mysteries that this interstellar visitor has brought with it. The most advanced computational models are being put to the test in ways their creators never anticipated. Supercomputers that process trillions of operations per second are being dedicated exclusively to simulating possible scenarios that explain the anomalous behavior of this comet. And yet, each simulation that comes close to replicating one of the observed anomalies fails miserably when attempting to replicate the others. It's like trying to solve a puzzle where the pieces change shape every time you think you've found where they fit. A frustration for scientists, no doubt, but also an unprecedented opportunity for the advancement of human knowledge. Dr. Alejandro Mendoza, an astrophysicist from a prestigious Mexican university who has dedicated his career to the study of minor objects in the solar system, recently expressed his perplexity in terms that resonated deeply in the academic community. According to his words, 3I Atlas represents the type of challenge that only appears once every several generations. A phenomenon that forces us to question not only the specific models of cometary behavior, but the fundamental assumptions upon which those models were built. And those fundamental assumptions include some that we have taken for granted for centuries. That celestial objects obey exclusively the laws of physics as we understand them. That any apparently anomalous behavior can eventually be explained through natural processes that we simply had not previously identified. That the universe, although vast and mysterious, operates according to principles that the human mind is capable of understanding and quantifying. 3I Atlas is putting each of those assumptions to the test in ways that are profoundly uncomfortable for some and extraordinarily exciting for others. You know, friends, there is something that particularly fascinates me about this whole situation, and it is the way this comet is forcing us to be humble. For decades, perhaps centuries, we have assumed that we understand how the cosmos works, that our equations can describe any phenomenon if we simply gather enough data. But here is 3I Atlas, arriving from the depths of interstellar space, and essentially telling us that maybe we don't know as much as we thought. Doesn't that seem fascinating to you? Doesn't it seem, in a way, liberating? The projected encounter with Jupiter's Hill radius in March of the year 2026 has generated an unprecedented level of anticipation in the global astronomical community. The planet's main space agencies are already coordinating efforts to ensure that multiple instruments will be pointing toward that region of the sky when the moment arrives. The most powerful space telescopes are being programmed to divert their attention from other scientific projects during the critical days of the encounter. Ground-based observatories on all continents have reserved observation time months in advance. Even networks of amateur astronomers, like the team that captured the first anomalous images from Mexico City, are preparing their instruments to contribute to the global coverage of the event. But the question that everyone is asking, from the directors of space agencies to the enthusiasts who observe the sky from their backyards, is what exactly will happen when 3I Atlas crosses that invisible gravitational border that marks Jupiter's domain. The possible scenarios are multiple, and each one has profound implications for our understanding of the universe. The most conservative scenario suggests that the comet will simply pass near the limit of the Hill radius without being captured, continuing its journey toward the outer solar system with a slight modification in its trajectory caused by the gravitational attraction of the gas giant. It's what physics predicts for most encounters of this type, and it's what most scientists would expect to observe under normal circumstances. But the circumstances with 3I Atlas have long since ceased to be normal. A second scenario contemplates the possibility that Jupiter's gravity captures the comet, at least temporarily. This would mean that 3I Atlas would go from being a transitory visitor to becoming a semi-permanent resident of our solar system, orbiting Jupiter or the Sun in a completely new trajectory. Scientists could then study it for years, even decades, with increasingly sophisticated instruments. A third scenario, more dramatic, involves the possibility of fragmentation. Jupiter's gravitational tidal forces are immense, capable of tearing apart objects that get too close. If 3I Atlas passes close enough to the gas giant, it could break into pieces, revealing its internal structure in ways that would be impossible to observe otherwise. And then there is the fourth scenario. The one that no one wants to mention in formal academic publications, but that circulates in private conversations among researchers who have spent too many nights analyzing the anomalous data of this interstellar visitor. The scenario in which 3I Atlas does something completely unexpected, something that none of our models can predict, something that forces us to reconsider everything we thought we knew about the nature of objects that travel between the stars. Do you know what intrigues me most about this encounter with Jupiter, friends? It's the fact that the trajectory adjustment pointed precisely toward that destination. Not toward the Sun. Not toward Earth. Not toward any other planet in the system. Toward Jupiter, the largest, the most massive, the one with the greatest gravitational influence after the Sun itself. If one wanted, hypothetically speaking, to study a planetary system, using the gravity of its largest world to significantly modify a trajectory would be the most logical option. I'm just saying that. I'm not drawing conclusions. I'm just observing coincidences that, let's admit it, are quite extraordinary. The history of interstellar objects detected so far is brief, but revealing of how little we know about the messengers that cross the void between the stars. Oumuamua, the first, appeared and disappeared so quickly that we barely had time to capture basic data about its nature. Its elongated shape, its inexplicable acceleration, its lack of a cometary tail despite its proximity to the Sun, all those factors generated speculations ranging from the scientifically conservative to the frankly fantastic. 2I Borisov, the second, behaved in a much more conventional manner. It was clearly a comet, with a visible tail and behavior that fit reasonably well into our models. Scientists breathed a sigh of relief seeing that not all interstellar visitors were as enigmatic as Oumuamua. And now comes 3I Atlas, combining elements of both predecessors in ways that defy simple categorization. It has a tail like a conventional comet, which distinguishes it from Oumuamua, but it exhibits anomalies in its behavior that recall, and even surpass in some aspects, those of the first interstellar visitor detected. It's as if the universe was sending increasingly complex messages, increasingly difficult to ignore, increasingly impossible to explain with the conceptual tools we have developed so far. The question that many researchers ask themselves in private is whether we are prepared for the answers we might find, not from a technological point of view, but from a philosophical and cultural point of view. For centuries, humanity has debated whether we are alone in the universe. The answers have varied from the religious certainty of our uniqueness to the probabilistic conviction that, in a cosmos with hundreds of billions of galaxies, intelligent life must exist in countless other worlds. But debating abstractly about the existence of other intelligences is very different from facing concrete evidence of their presence in our cosmic neighborhood. This is the stance that should always be demanded, friends. More open data, more independent replication, and fewer attempts to prematurely close the debate. Science is not a dogma, it is a process of questions, of exploration, of humility before the unknown. Does it not seem to you that sometimes we forget that? That we cling to what we believe we know instead of keeping an open mind before the new? Well, my friends, Felipe Suarez here, signing off for now. Before I go, I want to ask you a very special favor. If you liked this story, if it made you think, if it reminded you of a night looking at the stars with someone dear to you, leave me a comment telling me that experience. I love reading your stories, because they remind me that I am not alone in this passion for the universe. And subscribe to the channel so you do not miss any news about 3I Atlas and all the mysteries of the cosmos. See you soon, compadres. Take care and keep looking up.